So there are two ways that we could deal with the fact that we have to connect the dots in order when we add the confidence bands to the plot. So one way would be to, as I've done here, take the vector called voltage and put it in the order of the voltages, and then take the vector of lower bounds and put that in the same order. So just to show you how that would work, I've printed out the vector called voltage here, and you can observe it's already in increasing order, right? This is already in order. So actually, I don't necessarily have to order here. I'm doing it in order to show you how you would do it if you didn't already have it in the right order. But suppose this vector said 30, 32, 26, 38. If it wasn't in order, then you would be connecting the dots in the wrong order were you to not fix this. So when I say order voltage, let me just run this piece. What it does is it tells me the order I should put the data points in so that the data points will be sorted. So when I say voltage bracket order, again, it puts the voltages in order, and they already were in order, but if they hadn't been, they now would be. Then what this does is it takes the lower bounds, the vector of lower bounds, which is a vector, right? There's one lower bound for each data point, and it puts them in the order of the voltages. Now, crucially, I'm not taking the lower bounds and putting them in the order of the lower bounds. Right? If you take one vector and sort it, and a different vector and sort that one, where again the first vector is sorted from smallest to biggest on that vector, and the second vector is sorted from smallest to biggest on that vector, that's not good, because then your two vectors might be in different orders, right? You lose the pairing of the x and y coordinates for the points that you're plotting. So we want to take both the voltages and the lower bounds of these intervals and sort them in the same way. In other words, order them so that they go from smallest to largest voltage. And so that's what we're doing here as well. See, so here the lower bounds sorted in the order of lowest to smallest voltage, and you can see that these are in decreasing order of the actual lower bound values, right? And that's because the lower bounds are decreasing as voltage is increasing. So if I run this line right here, you can see that what I've done is I have added the lower bounds of these confidence intervals to my graphic, and I can do the same thing for the upper bound. And there we go. Okay, so those are called confidence bands. And the idea is that for any particular value of voltage, so say like 30, right, then the width between these bands gives me a confidence interval for the predicted mean of log time when voltage is equal to 30. Note that I said type equals O here. When you say type equals O, it draws the points and also connects them. If I had type equal L, it would connect the dots without drawing the points. If I had type equals P, which is the default, it would make the points but not connect them. I mentioned this is one of two ways you could do it. Something that I'd rather have you do would be to reorder the entire data set, because it's awkward here that I had to use the word order 4 times in order to make these prediction bands. But if I go to the very top of my code file and just reorder the rows to begin with, right, then everything else I do will be in the correct order. So if I have some variable x, and here it's voltage, that I want the values to be ordered by, at the very top of my code file, I can create a new version of the data set such that the rows are in the desired order, and then I don't have to deal with the order any other time. That's what I suggest you do for your problem set. And if you realize halfway through your problem set that you needed to do that, remember that our code is reproducible, so it's no big deal, right? Go back to the top of your code, reorder the rows, and then you should just be able to run your code, assuming that nothing you did in the code depended on that order. So for example, if it's the Palm Beach data set, assuming that you didn't delete the row corresponding to Palm Beach by referring to its order in the data set, assuming you didn't do that, you should be able to go to the top, order by the variable you'd like to order by, and then you should be all set and not have to mention order for the rest. This piece of code does the same thing for prediction intervals. The only difference between this and what's above is that the width of the intervals is going to be wider according to the correct expression for drawing prediction intervals. So here are the prediction intervals. You can see that they're wider, right? Because they're meant to contain 95% of the data points. So you can see that that's true here, right? The prediction intervals are much wider, and if I have a new data point, right, the idea is now if my new data point has voltage equal to 30, this range is supposed to be arranged such that there's a 95% chance that that actual data point, the new red dot, will go between those bounds, which looks like it's reasonable here. That's prediction bands and confidence bands. The last thing I'm going to show you from this code file is about residual versus fitted value plots. Now, a residual versus fitted value plot is a graphic that can help you check the assumptions of a linear regression. The truth is that when you have a simple linear regression with only one predictor, it's actually not that helpful to have a residual versus fitted value plot because it doesn't show anything that you can't already see from a scatter plot, as you'll see when I run this code in one moment. However, when you have multiple predictors, like if you have not just X predicting Y, but X, Z, and W predicting Y, you can't really make a simple scatter plot, but you can't make a scatter plot with all three predictor variables on the same axis. And so the nice thing about a residual versus fitted value plot is that you can always make one in order to check the assumptions. So just to repeat that, a residual versus fitted value plot, which I'll show you how to make right now, is really helpful when you have multiple predictors for checking the assumptions of a regression. When you have one predictor, it's kind of redundant. Okay, so let me make this picture, right? I'm taking off the bands because we're talking about something else now. Here's my picture, right? My data points and my predictions. What am I going to do? I'm showing you how to get from this picture to a residual versus fitted value picture. Okay, I'm trying to, I don't know if you can see the picture of me, but I'm trying to move it out of the way. There we go. Okay, so the first thing I'm going to do is I'm going to change the x-axis so that instead of reflecting the voltages, it reflects the fitted values of voltage. What's a fitted value? It's the prediction of y. So instead of 26 as the x coordinate for these data points, instead I'm going to use, looks like the fitted value for these is about 5.8 or something. Instead of 28 for these data points, I'm going to use the fitted value here, about 4.5. Instead of 30 for the x coordinate of the scatter plot, I'm going to use something like, looks like about 3.5, something like that. So I'm still going to have these, in the next plot, these vertical lines of red dots, and the y-axis is going to remain the same. But again, instead of taking these vertical strips and plotting them at 26, 28, 30, 32, I'm going to plot them at 5.8, 4.3, 3.9. And the reason to do that is that if I had more than one predictor, right, then I don't know which predictor to put in the x-axis, but I will always have fitted values, just one for each data point. So this is going to be the same graphic. Watch it change. Same graphic. All I'm doing is changing the x-axis from voltage to fitted values. Okay. So the order reversed, right? Because we had a decreasing order. So the smallest voltages ended up having the biggest fitted values. So here is the set of voltages that were smallest, et cetera, et cetera. But the vertical pattern of these points hasn't changed at all. So the pattern looks identical. But I've changed the x-axis from something that would only work if I have one predictor to something that was always possible no matter how many predictors I have. But I haven't changed the pattern in the data. Now what am I going to do? I'm going to replace the y-axis by residual. So instead of showing the actual log time for each of these data points, I'm going to show the difference between each red dot and the black dot. So for example, for this red dot I'm pointing out here, its distance from the black dot is maybe like 0.3. So I'm going to write a 0.3 here. For this red dot here, its distance from the black dot is more like -2. So I'm going to have a -2 there. So the vertical strips of red dots are still going to be vertical strips because I'm changing the y-axis now. And they're still going to be vertical strips, but they are going to be just spaced apart the same amount they are now. All it is that the black dots are going to move to 0 and the red dots are going to be arrayed around 0 instead of around the actual fitted value. So watch the plot, see what happens. I'm going to go from this graphic to the next one, right? All I did was go back and forth between those. Let me see if I can do it like this. Ready? We had this, and then we had this, right? So what it does is it essentially takes the line and just swings it over so that it's a flat line. The black dots represent a flat line now, and now we have residuals. Okay, so the main point here is this is, unlike the initial scatter plot of voltage and log time, residual versus fitted value is something I can always make no matter how many predictors I have. How to use this to check for assumptions? Let's go back to the original scatter plot and think about how we did check assumptions there, and then we're going to see that you can check those same assumptions from the residual versus fitted value plot. So one assumption I want to check is linearity. In this case, my equation is the equation for a line. So the linearity assumption is that that equation is correct. So I'm just checking to see whether these black dots fall along a straight line. Okay, and here they do very nicely. We have the normality assumption. What we're essentially looking for there is symmetry. Are the red dots about as likely to be above as below the black dot for each vertical strip? And that's approximately true here. And then equal variance is the amount by which the red dots deviate from the black dot about the same in each vertical strip. And I think that's approximately true here as well. You can't check independence here without further information about how the data is collected. In fact, the fact that there's a group number, which probably means batch in this data set, suggests we might be a little bit worried about independence, but you can't check it from this graphic. Okay, so linearity, we check by looking at the fact that this is a line. Normality, we look to see if the points were symmetric above and below that line in vertical strips. And equal variance, I'm looking to see whether the points are vary the same amount around the black dot. So note that when I change how I'm organizing these dots in terms of X, and then slant the line so that it's a horizontal line, I can check the same things. So if I look for the mean value approximately of each of these red strips, the question is, like, do the means probably follow a line like this? And the answer is yes. You'd be able to see if linearity wasn't true if, for example, the data generally seemed to go in some curve pattern like that. Sometimes when you have a very nonlinear plot, you can see it that way. The residual plot will look like a curve. Okay. What about normality? Well, within each vertical strip, are the points about as likely to be above or below? Well, hey, these are the same vertical strips I had before, just organized differently, so I can check that in the same way. Yes, normality seems to approximately hold. What about equal variance? Is the amount by which the points are above or below the black dot about the same for each vertical strip? Well, again, these are the same vertical strips I had before, just organized differently, so I can check that in the same way. You can't see my fingers, but imagine I'm running my fingers across this plot on the bottom and the top, and I want to see if the range of these values is approximately the same all the way across. That's how you check for equal variance. So no matter how many predictors you have, the nice thing about a residual versus fitted value plot is that it's possible to create it, and then you can check linearity, normality, and equal variance as best as you can.